Hey everyone, welcome back to Math 261. This is Scott. Let's get started. We're going to pick up where we left off and explore now section 1.2, where we will explore in greater detail row reduction and what are called echelon forms. Row reduction and echelon forms. So first let's talk a little bit about matrices and what their ingredients are. So matrix ingredients. So first off, row is what we call the piece that goes this way. So rows go like so, whereas columns go like so. And then matrices are described by their size, and in particular how many rows by how many columns. So matrix size, you'd say m by n, and you do the by with like a little x. And m here would be the number of rows, and n would be the number of columns. So for example, 2 by 3 would be a matrix that has 2 rows and 3 columns. So it means it's got 2 rows and 3 columns. Okay, now that that is officially in the record, we can start talking about some of the more intricate elements of matrix orientation. Now, what we will call a leading entry of a row. This refers to the first non-zero entry. If the row is all zeros, then you'd say it doesn't have a leading entry. All right. Now, echelon form, or row echelon form. Or row echelon form, comma, REF, particularly on calculators. So echelon form, or row echelon form, is a matrix that has the following 3 characteristics, so 3 properties. So the 3 properties are: 1, if there are any rows that are all 0, those have to be on the bottom. So any rows of all zeros must be on the bottom. 2, each row's So each row's leading entry is to the right of the leading entries of the rows above it. So in other words, what that means is the leading entries are moving to the right as we go down. So in other words, as we move down, the leading entries move rightward. And then lastly, thirdly, below any leading entry, there are only zeros. Below any leading entry, there are only zeros. Now, as an example, echelon form or not. Let's look at an example of a matrix not in echelon form and then compare it with one that is. So one that is not in echelon form could be, for example, this. Let's say we had 3, 0, 4, 1, and then 0, 0, 3, 2. So right now, as of yet, there's nothing wrong with this. This would be in echelon form as written. However, if there was one more row and it was something like this, 0, 1, 1, 5, then if we look at where all the leading entries are, and we can indicate those just by putting a little box around them. So these are the leading entries. Then you can see that this fails both conditions 2 and 3. The leading entries are not moving to the right as we go down. It goes over here, but then it goes back over here. Also, you can see that below this leading entry, there are things besides just 0. So this is not echelon form. Alright. How about another example? Let's take B, which is the same matrix, but with the second two rows switched. So let's say we had same matrix, 3, 0, 4, 1, except now we're going to switch the order of the last two rows. So 0, 1, 1, 5, and then lastly 0, 0, 3, 2. So now, again, the leading entries are going to be put in the little boxes here. And now you can see that as we move down, the leading entries move to the right. There's nothing but zeros under each of the leading entries. And so this is echelon form. reason why it's called echelon form, by the way, is the word echelon literally means like a staircase. And so you'll notice that what we are making here, each stage, it's progressing like a staircase. It's kind of an upside down staircase if we consider these two the steps. But if you're looking at it from the perspective of the zeros, we have a little staircase of zeros down in the bottom left corner. But anyway, so echelon form is what we were trying, although we didn't call it that, but it's what we were trying to get our matrices into in the previous section in order to solve the systems. However, there's a better, upgraded version of echelon form, which is called reduced echelon form. Reduced echelon form, or also called reduced row echelon form, which is abbreviated, especially again in calculators, as RREF. So this has all of the properties of row echelon form, just regular echelon form, but also it's got two more properties. So it says this is a matrix already in echelon form, but with two additional properties. So we already had three properties for echelon form, so then it's got those three properties plus two more. So property 4. Each leading entry is 1. So each leading entry is a 1. And these leading ones, we already know that they have only zeros beneath them, but they also have only zeros above them. So each leading one has zeros above and below. And below it. So for example, could be something like this. Let's say we had 1, 0, 0, 2, 0, 3, and then let's say we had 0, 1, 0, 1, 0, 5, and then let's say we had 0, 0, 0, 0, 2, 2. Oh, sorry, 1, 2. 1, 2. So then if we look at the leading entries, it'll be there, there, and there. It goes row by row. Each of the first non-zero entries in a row is a leading entry. And you'll notice that they make a little staircase, but also you will notice that each of these boxes contains just a 1, and below each of these ones are only zeros, but also above each of these ones are only zeros. Now over here, you'll notice that there are other things going on in the meantime, but that's not really any of the business of reduced echelon form. The business of reduced echelon form is that if you look at all the leading ones, They have zeros below them, zeros above them, and they all progressively move to the right as you go down the matrix. So that's what reduced echelon form or reduced row echelon form or RREF comprises. Now, one thing to note about these reduced echelon forms, or RREF, is that they are unique, whereas echelon forms are not. So note, your book calls this a theorem, but since we're not going to be proving it, we're just going to be stating it. It's more honest for us to just call this a note. So note, although a given matrix may have many row equivalent versions in echelon form, each matrix has a unique reduced echelon form. So what that means is, if we do row operations, you and I, each on the same matrix, we may both be able to get them into echelon forms without agreeing, but if we try to reduce it so far as to get it into reduced echelon form, then at that point we will start agreeing. Now, let's discuss how we would go about finding the reduced echelon form for a given matrix, and then we'll discuss why we would even do that. So the row reduction algorithm. Also, this is sometimes called Gaussian elimination, named after Carl Friedrich Gauss, who was one of the great mathematicians of the 19th century. He was considered, even in his own time, to be one of the greats. In fact, when the Pope needed to determine when Easter would fall for the foreseeable future, he went to the greatest mathematician alive, who was Gauss. So Gauss did a lot of things. One of them was he was one of the first people to articulate this particular algorithm in the modern era. So we can also call this Gaussian elimination or Gaussian row reduction. But anyway, so here are some of the things that we need to define. So first off, pivot. So pivot is what we're going to use to refer to a leading one. So a leading one or leading entry may not start off as a one, but eventually it will end up one. Pivot position so this is the location where a pivot belongs, and then there's a pivot column. So this is a column that contains a pivot. Alright, now the basic idea behind the row reduction algorithm is the following. So the idea is that you want to work your way from left to right. Work your way from left to right. Choose. Choose a row to move into pivot position. And what you're going to use to choose this is based on the coefficients, how convenient they would be for scaling, things like that. So based on the coefficients. Okay, now use that row to clear the entries above and below it, and you can scale it down to 1 whenever it is convenient to do so. But so use that pivot entry to clear all the entries above and below. And then, whenever it's convenient, scale the pivots to make 1. Whenever convenient. So most likely, this would be something that you would do at this point when you were using it to clear the entries above and below. But really, the driving force is your convenience. So whenever convenient, scale the pivots to 1. Now note about this procedure. There's nothing very cut and dried about it, nothing very hard and fast, but the important thing, so you can be a little bit flexible when you're applying this, however, you have to make sure not to undo all of your hard work from before. So note, you can be flexible in your row reduction. But be careful not to counterproductively mess up columns that were already cleared out. So that's the most important thing. Just make sure that you don't accidentally undo some of the work that you've done already by counterproductively unclearing something that you all had already gotten pretty well squared away. Alright, enough talk. Let's get to work and see what this will look like. So let's try an example of this and see how it works in practice. So an example, and this is a nice big example, is what? 1, 2, 3, 4, 5, 6. So it's a 6 by 3 matrix. I'm sorry, a 3 by 6 matrix, I should say, which means 3 rows, 6 columns. And the first column is going to be 0, 2, 3. So 0, 2, 3. The next column is going to be -3, -6, -7. The next one is going to be 6, 8, 8. The next one is going to be -6, -6, -5. The next column is going to be -4, +4, 8. And the last one is going to be 5, 10, and then 9. So here we've got a nice big matrix, and you'll notice it is not currently in any kind of echelon form. It's not in just regular row echelon form or in reduced row echelon form. So what we want to do now is we want to look at it and think about where we want our pivots to be. So first off, in the first column here, so the first column, by the way, there will always be a pivot in the first column unless it's all zeros. If it's not all zeros, then there will be a pivot, and other columns, who knows, but the first column, if the first column is not all zeros, there has to be a pivot in it. So we will identify the target for our first pivot, and so we can't actually scale that 0 up to a 1, that's impossible. But we could scale that 2, or we could scale that 3. So one of these two rows is going to have to be moved into the first spot. Now you look at the entries of them and you make a decision about which one will be easier to deal with. So if we wanted to scale this one to make that into a leading 1, that would mean we'd be dividing it by 2. Now if you look at the entries of it, they're all even. So we could divide them evenly by 2, no problem. Here, however, if we wanted to make this one, if we wanted to scale this one, we'd have to divide them all by 3, and these aren't all multiples of 3, and so it's not going to be as convenient. So you look at the coefficients and you decide based on that what would be the most convenient of the pivots. So the other entries in this row would be very convenient to do, and so what we're going to do, and I'm going to actually put the two steps together on this because I don't want to rewrite the whole thing over and over and over again every time I do one little thing. So the two steps that we're going to do is we're going to switch row 1 and row 2, and then I'm going to, while I'm at it, make row 2 into 1/2 of its former self. Now, I like to put a little asterisk by the ones that mean the new row 2. Actually, you know what? Let's not be heroes here. This is our first first trip out on this particular topic, and let's not go nuts on trying to be slick with shortcuts and whatnot. We're just gonna end up messing ourselves up if we try to take on too much at once here. So let's just do this in 2 steps. So I'm just switching row 2 and row 1 around. It's gonna be 2, -6, 8, -6, 4, and 10, and then 0, -3, 6, -6, -4, 5, and then here the last one is still going to be 3, -7, 8, -5, 8, and 9. Most important step in this is to write these things down correctly without a typo. So if I have done that, which looks like I have, then we can proceed on. And so now at this point, what I'm going to do is I'm going to take my new row 1 here and I'm going to replace that by 1/2 of itself, so I'm scaling it. And that's going to be 1, -3, 4, -3, 2, and 5. Next we're going to have 0, -3, positive 6, negative 6, negative 4, positive 5, 3, negative 7, 8, negative 5, 8, and 9. Now, what we want to do is use this pivot that we've got here. So this is our pivot that we're working with. We're going to use the pivot to clear the entries below and above it. Now, currently there are no entries above it, and the first entry below has already been cleared. So that means our only step now is that row 3 is about to get itself cleared a little bit by doing negative 3 times row 1 plus old row 3. So 1, negative 3, 4, negative 3, 2, and 5. We're just copying and pasting row 1 as it was. Nothing is changing about it. Row 2 is also staying the way it was. So 0, negative 3, 6, negative 6, negative 4, and 5. And then what we've got down here is going to be 0, negative 3 is going to make positive 9, add negative 7, and it's going to make positive 2. Negative 12 plus 8 is going to make negative 4. And then what else here? So we've got positive 9 plus negative 5 is going to make positive 4. We're going to have negative 6 plus 8 is going to make 2. We're going to have negative 15 plus positive 9 is going to make negative 6. Okay, so there's where things stand now. Now the next thing that we have to consider is the next pivot position. So clearly it's going to be either this one or right here is where the next pivot position is going to be. But we have to make a decision about whether we are happy to keep it as a negative 3, or we would prefer to switch the row 2 and row 3 around in order to put this one there. Now, if we look at this row, it actually at first it looks like that would be a pretty good one. We can scale it down, and that's going to be nice, but then not so nice. Whereas with this one has a leading entry currently of 2. When we scale that one down, it's going to be dividing by 2, which is convenient for all of its entries. So all of its entries are even, which means dividing by 2 is a breeze, and so we will opt for that one. So this is our chosen pivot, which means that we're going to need to swap it into the right position. So row 2 and row 3 are getting switched around. Okay, 1, negative 3, 4, negative 3, 2, and 5. And then we're going to have 0, 2, negative 4, 4, 2, and negative 6. And then we're going to have 0, negative 3, 6, negative 6, negative 4, and positive 5. So we're just switching row 2 and row 3. And at this point now, it's good for scaling. So this is still a desired pivot here. So now for scaling, we'll take row 2 and we'll replace it by half of itself. 1, negative 3, 4, negative 3, 2, and 5. 0, 1, negative 2, 2, 1, 3, and then 0, negative 3, 6, negative 6, negative 4, positive 5. Alright, now, at this point, we want to use this pivot for the purpose of clearing the entries above it and below it. So to clear the entries above it, that means row 1 is going to be replaced by 3 times row 2 plus regular old-fashioned row 1. And while we're at it, row 3 is going to be replaced by 3 times row 2 plus regular old row 3. So we've got 1. Okay, so now it's going to be 3 times this plus that. So it's going to be 0, which is the goal. And then we're going to have 3 times negative 2 is negative 6 plus 4 is going to make negative 2. 3 times 2 is 6 plus negative 3 is 3. 3 times 1 is 3 plus 2 is 5. 3 times 3 is 9 plus 5 is 14. Now this next one is not undergoing any changes. So it's still going to be 0, 1, negative 2, 2, 1, 3. Now down here we are going to be doing the same operation we did upstairs. So now we're going to have 0, and now it's going to be 0, which is the goal. And now it's going to be, so 3 times negative 2 is negative 6 plus 6 is going to make a 0. So then we're going to have 3 times 2 is 6 plus negative 6 is going to be a 0. We're going to have 3 times 1 is 3 plus negative 4 is negative 1. And then we're going to have, finally, 3 times 3 is 5. So it's the same as one above, so it's going to be 14. And, oh, wait a second here. There's a mistake. Can you see it? So right here, the second row, that should have been a negative 6, which meant that was going to be a negative 3. So, okay, some damage control here. So what's that going to make this next one? So everything is going to be good except for what happened in the last column there. That is not good. So the last column, so that should have been negative 9 plus 5 is going to be equal to negative 4. So negative 9 plus 5 is equal to negative 4. And same thing down here. Sorry about that. These things happen. It's a long, laborious process, but luckily this is a procedure that is so systematic that even something as stupid as a computer is capable of doing it. So don't worry. We'll figure out at a later point, when we've earned the right to do so, how to get computers to do our bidding. Alright, now looking at where we stand, this is now the new pivot of interest to us. And so we're going to want to turn it into a 1, and we're going to want to use it to clear the things above it. There is nothing below it. So what that gives us is, first off, row 3 is going to be just negative row 3. It seems kind of silly and pointless to go rewriting the whole matrix just to accomplish this one little thing, but you can see even when you do take your time and watch your step, it's still very easy to make mistakes. So just be careful out there, folks. This is a dangerous game we're playing. So 0, 1, 2, 2, 1, 3, 0, 0, 0, 0, positive 1, and positive 4. Okay, good news. Good news. Now we are back on track, and all that's left here is for us to use this pivot to clear the things above it. So this is going to be the last step of it. Let's see if we can squeeze it in here on this one last piece of paper. Nope, don't be a hero. Don't be a hero. That's the watchword of this class. Just be careful out there. Take your time, do your steps properly. Okay, so now row 1 is going to be replaced by former row 1 plus negative 5 times row 3. Okay, so there's that, and row 2 can be replaced by negative row 3 plus old row 2. Oops, row 2. So, tiring, it's a little easy to make mistakes, that's why you gotta be extra vigilant. Okay, 1, 0, negative 2, 3. Nothing, notice by the way that as long as we're talking about the columns that have zeros on row 3, none of the entries on either of the other two rows are changed in those particular columns. So then we just go down to where we start having entries. So starting here, negative 5 plus 5 is 0, which was the goal. Negative 5 times 4 is negative 20, plus negative 4 is negative 24. And then we have 0, 1, negative 2, 2, 1, and negative 3. And, sorry, I forgot to clear that. So it's going to be 0. And then it's negative row 3, so it's going to make that into a negative 7. Sorry about that, getting a little tired here, making some mistakes. That's why I've got you here to keep me on my toes. 0, 0, 0, 0, 1, and 4. Okay, and there it is now in reduced echelon form, or reduced row echelon form. These are the three pivots, and you'll notice that above them and below them are only zeros. The other three columns do not contain pivots because they don't have any leading entries in those rows. Now, what is the connection of this to linear systems? So back to systems of linear equations. So as an example, something just to chew on, let's take a linear system that looks something like this. Negative 3 x2 plus 6 x3 minus 6 x4 minus 4 x5 equals 5. So that's the first equation. Oops, sorry, it's a little off screen there. So I said again, negative 3x squared plus 6x, negative 3x2 plus 6x3 minus 6x4 minus 4x5 equals 5. And then as our next equation, take 2x1 minus 6x2 plus 8x3 minus 6x4 plus 4x5 is equal to 10. And then the last one, 3x1 minus 7x2 plus 8x3 minus 5x4 plus 8x5 is equal to 9. Okay, now what is the point of this system that I just gave? Well, if you'll carefully compare the coefficients in this system with the matrix that we were just dealing with, you can see that the augmented coefficient matrix of this is actually the one we've been dealing with. So this is actually has the augmented matrix 0, negative 3, 6, negative 6, negative 4, 5, 2, negative 6, positive 8, negative 6, 4, 10, 3, -7, 8, -5, 8, and 9. Only now, the only difference between this and the matrix from before is that the optional bar could be written in here, now that we know that's auctioned. Now, here's how we can say the result of what we just did. So RREF version of this is equal to what we just found. 1, 0, -2, 3, 0, -24. 0, 1, -2, 2, 0, -7, 0, 0, 0, 0, 1, 4. And that last column represents all the constant terms. So what this means is, by putting it all in the matrix form, we were able to go step by step, get here, and what we now have is the system of equations that has been boiled down into this much simpler version. Now the equations here, the equations of this equivalent system, that it's totally equivalent to the one we started with, would now just look like x1, and I'm just going to put a missing space, minus 2x3 plus 3x4, put a space for the missing variable, equals -24, x2 minus 2x3 plus 2x4 equals -7, and meanwhile x5 is equal to 4. Now we can start to describe what's going on in this situation by looking at the difference between the variables that do versus don't make pivots. So the variables that do have pivots are called basic variables, and the ones that do not have pivots, do not correspond with pivots, are what are called free variables. So note the variables with, or let's say, whose columns have pivots are called basic variables. Let's see, and those whose columns don't have pivots, whose columns don't have pivots, are called free variables. Now, once we have done the business of getting the matrix into reduced or echelon form, we can determine which variables are basic, which variables are free. So here, x1, x2, and x5 are basic, whereas x3 and x4 are free. Now, once we have these all laid out, then our goal is essentially to express all of the free variables in terms the basic variables in terms of the free variables, and then the free variables will serve as parameters. So for our solution sets, express all basic variables in terms of the free variables, which means basically that the free variables will be the parameters that will characterize the family of solutions. So this makes the free variables parameters for the family of solutions. So what that means basically is you give me choices of the values of the free variables, and those will cause the solution, or the values of the basic variables, to follow suit. So that means for each combination of values of the free variables, there will be a different value of the basic variables. So then here, the way we would write such a thing is to go like this. So what you would do is you would take the equation x1 minus 2x3 plus 3x4. So that was one of the equations that we had, equals negative 24. So this, you would rewrite it with a basic variable in terms of the free variables. So you'd have x1 equals, and you just add everything, or you'd add or subtract to move everything to the other side. And so you'd have 2x3 minus 3x4 minus 24. Let's see, the next one was x2 minus 2x3 plus 2x4 equals negative 7, which means if we rearrange things, we would have x2 is equal to 2x3, and then minus 2x4 minus 7, and then of course we had x3 was equal to, x5 was equal to just 4, so that doesn't need anything else. Really, that's kind of unnecessary. And then the way we would typically lay it all out is as follows. So then we would give a general solution in this form. So what we would say is just basically what we've got there, just all laid out nice and neatly. So we'd say x1 equals 2x3 minus 3x4 minus 24. x2 is equal to 2x3 minus 2x4 minus 7. And then here, you'll see as the course develops, we'll be a little bit more flexible in how we write this. But for now, we will just say x3 is free, x4 is free. So you'll see that there are other ways we will write it later, but in the meantime, we're just going to write it like that. And then lastly, we'll say x5 is equal to 4. So this would be the general solution. All right. Now, let's think about what this all means in terms of consistent, inconsistent, infinitely many, single unique solution, things like this. So here is a theorem. Your book calls it theorem 2, but there's no point in really numbering these because we're not going to refer to them by number in the future. So a linear system, I should say a system of linear equations, but we'll frequently also call that just a linear system, but we'll keep the language consistent here. A system of linear equations is consistent if and only if there is no row of the RREF, so that was again reduced augmented form, reduced row echelon form. There's no row of the RREF that, I should say, of the augmented matrix. Augmented matrix. By matrix, I mean the coefficient matrix of the form 0, 0, dot, 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 0, 0, zeros, a bunch of zeros, followed by a B, where the B here is not equal to 0. So we can't have any row that looks like this in the augmented matrix when you row reduce it. Furthermore, and if a system is consistent, there will be a unique solution if and only if there are no free variables. Conversely, and there will be an infinite family of solutions whenever there is a free variable. Alright, so that's that. Now we'll discuss again a little bit more detail. In fact, actually, we're going to discuss all of this again in more detail as we progress through the course and improve our depth and breadth of understanding. But basically, the way to think of these free variables is they are the parameters that will give the basic variables their values. So looking up here, the reason why these are free variables is they can literally have any value. You can just pick out of the sky any value you want for x3 and for x4. And then based on those values, that will determine what the values will be for x1 and x2 according to these equations. As for x5, it has to be 4. Other than that, these other two will have values that depend on what you choose for x3 and x4. And as for x3 and x4, you can choose anything you want. That's why they're called free. All right, but that about does that. That is the end of the of section 1.2 for Math 261. Until next time, bye.